Lab. From John's video at the 1730 mark, I get the following information where the black tick marks are 1 centimeter apart according to John. You could do one of two things here. If you have a tablet, you could come in here and pick two spots. So let's say I pick this spot here and this spot there, so I'm going from the middle, and I know that that distance according to John's scale is 1 centimeter. If you don't have a tablet, you can just print this out. What I did here is that I know this is 1 centimeter. This I do not know what it is. Even though it's an image of a ruler here, what I need to do here is that I'm going to stretch this guy out. So I'm going to pick the centimeter mark, and if I shrink this down, you could see that I can play with this till I get about 1 centimeter. So assuming that I scale this to 1 centimeter, then I could measure the fringe separations between using the scale right here. But so then that means I could come in, if I compare this to the scale that John has, looks like it's not so good, but I'm going to say that that's okay. I now have a scale to measure the separation between the bright fringes and the dark fringes. On the other hand, if you print out this image on paper instead, John's scale will not be set to 1 centimeter units. So to get the right numbers, you must use a conversion factor to measure the fringe separation. Now let's look at this ruler here. Let's say that this is your actual ruler, and if I compare 1 centimeter to the centimeter that's on here, you don't get the same value. So I need to set up a conversion factor. So what you're seeing right here is that 0.6 centimeters or 0.6 units on John's scale is 1 centimeter on an actual ruler. Therefore, the conversion factor is 0.6 units equals 1 centimeter. Then I'm going to use this ruler to make all the measurements on the fringe separations and then convert to get the right units. Now I'm going to set up an Excel table to organize the information for collecting data. Okay, so here it is. So I have a column of the M value, which is the fringe, and you can see that I'm going from 0 to 5. We measure everything relative to MC equal to 0, so this is darkened out because we don't have a value there. That is the actual 0. And then you could see here that I have delta Y bright, delta Y dark. These are the units that will have to be converted into centimeters. Here's the image of the interference patterns from John's video. So the first thing I'm going to do here is that I'm going to label each of the fringes. So if this is MC, this is the central fringe, which is at 0, then I'm going to go 1, 2, 3, 4, 5. So the first thing that I want to measure here is I want to measure the location of the first fringe. What does that mean here? That means the distance from here to here is the separation of the bright fringes. So if I look at that number on my centimeter scale, it reads 0.6 units. Using the conversion factor that we just derived, you could see that this is actually 1 centimeter between that location right there. So now let's go to the next one. MC equal to 2. When I look at this scale, you could see that the distance that I'm going to be looking at is the distance between these two fringes. So the way I'll deal with that here is that note that distance is 1.2 units, but those are 2 fringes. So then if I have my scale again, you could see that this is again going to read 1 centimeter between these fringes. Moving a little bit faster, if I look at the third fringe, that is from the 0 to the third MC value, I measure 1.75 units divided by 3, then my conversion factor, and I get 0.97 centimeters. Now let's go put this all into Excel. So now if I put in my values into Excel, I can get an average, 2 times the standard deviation of the mean, and then I have my confidence interval right in here. Now you go and measure the separation between the dark fringes on the left side and record your values in this Excel table. Are the separation between bright and dark fringes the same? The way we answer that question is we look at distribution curves. Let's say that this is my confidence interval for the bright separation of fringes. Let's say that after you make your measurements for the separation of the dark fringes, you get this distribution curve. The fact that these two curves are overlapping tells us that they're consistent with each other. So overlapping confidence intervals means the bright separation and dark separation of the fringes have the same separation distance and therefore consistent with each other. Predicting the wavelength of a green laser. Using your delta Y bright average, calculate lambda theory. That is, using this small angle approximation of the fringe separations, predict what Y theory is. To calculate the standard deviation of the mean, we must propagate the uncertainty in the fringe separation to the wavelength. We know that for the small angle approximation that this relationship is true. The relationship big D over little d is a constant, and if it's a constant, then that means it must be proportional to the wavelength. So the uncertainty in the separation of bright fringes must also be the uncertainty in the wavelength. So therefore, because these guys have separate units, you'll see here that the uncertainty in delta Y divided by delta Y is unitless, but since these guys are directly proportional to each other, then the uncertainty in lambda divided by lambda, these guys should be exactly the same. Therefore, the uncertainty in lambda is equal to lambda times this ratio of uncertainty of delta Y over delta Y. This lambda value is calculated already up here. So once you solve for that, you plug in lambda. These two values are already in your Excel table. All you got to do is just plug them in. The spread in the wavelength is then lambda plus or minus 2 sigma. So if I look at that confidence interval, if lambda accepted, which is 532 nanometers, is outside the confidence interval, then it's not consistent with your predicted value. If it lands within the confidence interval, then we say it's consistent. So after you make the measurements, then determine whether it's consistent or inconsistent. Predicting the wavelength of the green laser using a slit separation of 0.50 millimeters. So this is from John's video again. So then repeat the exact same thing that we did, but this time focus on calculating the wavelength by measuring the dark fringes. Following the previous process here, identify the central max, label MD values for the right side of this pattern, use Excel in order to get the average and standard deviation of the mean of the dark fringe separations, then predict lambda. The last thing you want to do here is that you want to compare the distribution curves for little d equal to 0.25 and little d equal to 0.5 millimeters. For those wavelength predictions, those two curves should overlap. Do they? Check this. Part 2, Intuitively Understanding Two-Slit Interference Patterns. From John's video, explain what happens to the fringe separations when you compare the wavelength of green light to red light. How do those patterns change? And then compare the pattern between a slit separation of 0.25 to 0.5 millimeters. How do those separations change? Use physical and mathematical reasonings to explain these changes and why they occur. These are the two images that you want to really focus on from John's video to answer these questions. Okay, have fun with the lab.